My name is Sanjay Radia. I've been working on the Hadoop project at Yahoo for the last 4 years. It has been a real blast. Very proud to be an employee, have been an employee of Yahoo. Yahoo's actually been very responsible and crucial for the success of Hadoop. Excited to be and the team at Hortonworks and take Hadoop to the next level as an open source Apache project. So Apache Hadoop has grown rapidly. It has charted a lot of new territories in features, in abstractions, in API, in incredible scale, in fault tolerance, in multi-tenancy, in operations. A lot of the early customers at Yahoo really needed a new platform that could solve problems that they could not solve otherwise. Okay, so it started off pretty small. And one of the smart things we did was to actually provide Hadoop as a service at Yahoo. And what they did was it let our early customers focus on their applications and their problems rather than trying to go to IT and say, look, I want to deploy this new Hadoop weird thing. Okay, so it really made the growth at Yahoo, the service offering Hadoop as a service was crucial to the growth at Yahoo. Today, you clearly see a dramatic growth in adoption and customer base, growth in the Hadoop ecosystem and applications. And what all this growth does is brings new requirements and new expectations. And what my talk is about is to see how we're going to be meeting these new requirements and expectations. Okay. So kind of quick overview, I'll talk about how we address issues from a different set of perspectives, from security, from SLAs, scalability, et cetera. And that'll be kind of the major part of my talk. And then I'll talk about a couple of very fundamental architecture changes that we are bringing forward in the next release of Hadoop on federation and MapReduce, and how these will actually fuel innovation and provide a much more rapid development environment. And then I kind of conclude with the community effect. So the early versions of Hadoop had actually no authorization, no authentication. We, in fact, waited till release 16 to add permissions. And this was really trying to address accidental deletes by a user. But very soon we found that as we started to move towards shared clusters with multiple tenants, many of them storing critical data, security was very important. And we see this also happening now for customers in the enterprise space, especially people using it for financial applications, that security is very important. In the release 2 or 3, we added security to both HDFS and MapReduce. And to the components like Uzi that go around it. And this was a very major effort done by Yahoo, about 10 years of effort in design and implementation, and a very important milestone for us. The other area that has actually been very important for customers is SLAs and predictability. And a lot of the early customers are just happy to have something like Hadoop to solve problems they couldn't solve otherwise. But a lot of the new customers were uncomfortable with shared clusters. Traditionally, the way they did things was they would buy dedicated hardware that was, the capacity is configured around the peaks that they expect to have. Although it had poor utilization, they felt very comfortable with the fact that they had control over that hardware. They owned it. So the challenge for this to have shared clusters was how do we do this? And so what we did in the release 20 was to provide at Yahoo what we call the capacity scheduler. And what it does, it guarantees capacity in a multi-tenant shared environment. In fact, it's almost like having your dedicated hardware. So we don't actually literally give you specific hardware, but we guarantee that capacity. So each organization is given one or more queues with the guaranteed capacity. They control, the organization controls who's allowed to submit jobs to that queue, set the priorities of jobs within the queue, and in fact, even create sub-queues, okay? So it's almost like having your dedicated hardware, but it's actually in some ways better. unused capacity that you are not using can actually be given to other queues and other projects. Okay, and the reason is often better is because when you're in a crunch, okay, because either your data arrived late and now you need to process it faster, you actually have access to the unused capacity. Okay, and this works very effectively if the peaks of the various tenants are at different times, or, for example, you have mixed production and non-production jobs, so you can kind of cut back on the non-production when you have a real demand needed on the production jobs. Okay. There's actually another scheduler called the Fair Share Scheduler, whose focus is really more fair sharing of the resources, but it also has notions of pools to kind of guarantee some of the capacity. Okay, and this has actually worked out extremely well for us. And we continue to make improvements to this capacity scheduler to things like preemption to give you much better SLAs, okay? The other area that we have focused on a lot is clearly on scale. And the early work we did was really based on a single name node master, a single job tracker. We kept all the namespace in memory, and it was a very, very simple locking feature. And we were able to actually rapidly scale this from 200 to 500 to 1,000 to 2,000, and now we are over 4,000 nodes of the largest cluster. And at that time, we focused more on vertical scaling, efficient memory usage, and the archive file system that we added. Okay, but for the very, very large clusters, there was a limitation on the number of nodes and storage that you could store. For customers with smaller size data, they should be okay with what is currently then in 20. Okay, the other thing was that the job tracker did not scale beyond 30,000 tasks. Okay, and needed a redesign. So in the upcoming releases, we've added much finer grain concurrency on the name node with the read-write locks. This was some of the work that the Facebook guys did. MapReduce Next, that next generation that Arun's going to talk about in the afternoon, is a complete rewrite of the MapReduce servers. Okay, they'll scale to over 100,000 tasks and about 6,000 servers. Federation, it really now, Hadoop basically has that horizontal scaling of storage and horizontal scaling of the I/O bandwidth. And we're now bringing kind of the similar thing to the namespace to be able to scale the namespace horizontally and to get to about 1 billion files. But we plan to go beyond that to have a name node that actually only keeps part of its namespace in memory and to go to much larger, say, trillion files. And it'll also bring the ability to restart the name node much faster because it does not need to bring all the namespace into memory. Okay. The other thing that is really crucial for customers is data integrity and availability. And I will first focus on HDFS and then kind of move to MapReduce. The early gains that we had was to focus on a very simple design, a very simple architecture, focus on storage fault tolerance, and actually use Java. So a lot of people are kind of surprised at why do you choose Java to write a file system? That's really dumb. It turns out that Java actually is responsible for the speed at which we have evolved. Java is responsible for the fact that we do not have pointer errors that lead to data corruption that are detected much later on. Okay, and the system has been able to absorb a lot more developers very quickly and do very, very fast, rapid development. Okay. And the places where Java, did not work well, we worked around that. For example, we pumped the data directly from the kernel into the socket as we pump the data out to the client. Okay, so the areas where you thought Java, it had some challenges, but it actually has been a very good decision. The other thing was overall simplicity of the architecture. So, for example, we chose to do a subset of the POSIX. We do plan to support atomic append down the road, but we decided not to do random writers. And I was talking to one of the original authors of the Google file system, on which Hadoop is based, and asked them, what would be any decision that they would revisit. And one of the things they said was actually random writers. They said that this was a feature that added a lot of complexity, and it was just not warrant the complexity. Okay, and so that was one of the decisions that they would revisit. And thankfully we did not go down that path. Okay. What we did was we focused on, for example, to use the OS's file system rather than use row disk. Okay. And it takes quite a while for file systems to stabilize, as you've seen with ext4. But the advantage we now have is that we're able to take advantage of other file systems. So for example, we would strongly consider moving and using ext4. And customers, in fact, can do that directly. Or XFS, or even ZFS if you're running on a Solaris box, for example. Okay? So it gives us that real advantage to take advantage of other file system technologies rather than having depended upon our own file system, of a row file system at the bottom layer. So I think that was one of the smart decisions. We focused a lot on the storage fault tolerance, dealing with node failures, replica, disk failures, and to do active monitoring and fix corruption of data. Okay. The name node does have a single name node master today. It does keep multiple copies of its state, both locally and remotely, and has checkpoints, and it restarts on failure. And that has been our approach so far. And so how well has this worked? Okay. So we were looking at some data over 2009 at Yahoo, and we had about 10 clusters, which had about 30 million blocks on that system. And over that 1 year period, we lost 650 blocks of the 320 million. And so we looked at it. Clearly, if your data is on those blocks, you're not going to be happy, even if it's only 650 blocks of 320 million. Okay, so 82% of these were abandoned files. And what happened was that in the original append that was in release 19 and 20, had a bug where it could not differentiate and realize that these were abandoned files, and therefore it reported it as a corrupt block. And we kind of had scripts that actually said, OK, these blocks are actually corrupted for this reason, and we can ignore them. Okay, 15% of our files that users created with a single replica, which meant that they didn't think this data was important enough. Okay, and in case of certain failures, you lost those. And then 3% of those 650 blocks. Okay, were due to 7 bugs that we fixed very quickly. Okay, so we take data integrity very, very seriously. Okay, and this is a pretty impressive record. Now let's go to availability. So over the last 18 months, okay, we have had 22 failures in 25 clusters. Okay, and these are all clusters that are very active, very large clusters with a lot of traffic and a lot of data. Of these 22 failures, only 8 would have benefited from an automatic HA failover. So that's a little bit less than 0.23 failures per cluster year. Okay, some of the failures, for example, that would have benefited is things like a hardware failure or a memory error, failure of power on a single power supply on this. So the name node is very, very robust, can take a lot of abuse. In fact, it is very resilient to when you throw very misbehaving applications against it. It does recover pretty well. And so kind of our response for these upcoming releases that we have a complete rewrite of the append and flush and sync in release 21, which addresses those 82% of the 650 blocks that we lost. We have a pipeline that recruits new replicas rather than just remove them. And this feature, by the way, is only really helpful for people doing where you have a slow appender. Okay. And we've done other work on improving the name node availability, much more faster startup. So it's about a 20-minute bounce on a 4,000 node cluster with about 15 petabytes of data. And with the federation, it actually allows the name nodes to be a lot smaller and therefore even faster. Okay, and federation also improves in isolation, so you can actually isolate your production customers from let's say, known production jobs, or put HBase on a different name node. So one of the questions people always ask is the single point of failure, and why did you guys wait this long for it? Okay, so we have started work on that. But before, let me just explain the failure rates. You saw the statistics. Did not demand making this a high priority. We really focused on the areas that were important to our customers. And the failure rates at Facebook are similar. For example, they do have the avatar name node, and they use it really to do hot failover during a lot of the upgrade cycle, okay? Which is really where they saw the issues, okay? And failover requires that all the corner cases be very correctly addressed, okay? So active work has started. Okay, Suresh and I have published a detailed design in HDFS 1623. Okay, this is a community effort. There are a whole bunch of JIRAs that are subtasks of these that have been filed, and we're working closely with engineers at Facebook, Cloudera, and eBay. There has been other work that's been done towards that. Of course, the avatar name node work that at Facebook. We have had a HA name node prototype using Linux HA at Yahoo. eBay has another prototype with the backup name node and a block report replicator that they have. And so we have actually doing a number of prototypes, and we have actually a design document that is moving forward. And it is a very high priority, and it'll happen in a dot release of 23, for sure. Okay. So let's go a little bit to MapReduce. Early gains in MapReduce was to deal with task and compute node failures. Unfortunately, the loss of a job, if a job tracker died, you lose the job queue. And we have completely fixed that in the next generation MapReduce. It is designed with fault tolerance and availability. Okay. There will be an HA version of the resource manager, the main scheduler, in a dot release of 23. But if you look at the resource manager, for example, if it dies, you can recover it by restarting or doing a failover, okay? And it recovers the state, of course. And even in the time when the resource manager is down, the degraded mode is actually fairly good. Apps continue to run with their current resources. They cannot get new resources because the resource manager isn't there. App managers can continue to reschedule within the current set of resources. New apps cannot be submitted or launched, and new resources cannot be allocated. So those are the only two degradations that you have, but the system cluster continues to function. Loss of app manager, it recovers, it's restarted, other apps continue to run. Tasks and nodes, they recover as before in the old MapReduce. Backward compatibility. So a lot of the early Hadoop had a philosophy of ship early, ship often, and get it out to our customers, okay? We have always maintained data and metadata compatibility, so you never, ever had to go and redo your data if, for example, if you upgrade to a new version of the system. But there were API changes and interface improvements, and the early customers, paid the price. A lot of the current customers, of course, will reap benefits from the more mature interfaces. But the increased adoption of Hadoop actually leads to much more increased expectations of backward compatibility. And we take this very, very seriously. In release 21, we did an interface classification of what is the audience of specific interfaces and stability tags. And it's really patterned after enterprise quality software process that I had used when I was at Sun and used in OpenSolaris and some of the processes we have at Yahoo. And so this really classified a lot of the interfaces extremely well, so we know what is public, what is internal, and what are the stabilities. And so it's a very important part of this work. We realize that interfaces will evolve, but we will maintain backward compatibility, and we will test for compatibility. A lot of our testing today is done using real Yahoo applications, okay? But we are looking at doing additional tests that run old jars to test for compatibility. A lot of applications are moving to Pig and Hive, which insulates them from the lower layers. The other part that we are going to provide is wire compatibility in 23 within the dot releases. So we actually will be maintaining the current protocol, the new protocol in 23, by carefully making sure that we do not delete old methods, or if we add, for example, a field to a data structure, a data type that's being passed, we will add a new thing. So this is using some of the traditional ways of doing wire compatibility, using our current Java serialization. But we realize that we are going to be moving to a different serialization technology, like let's say protocol buffers or Evro, and that this discontinuity will occur. And what we have is a design that shows how we're going to put adapters on client and server side to maintain protocol compatibility. So this is work that is going to go into 23. Moving into a different protocol serialization, that'll be something that'll happen in a later release. Okay. The other very important part, of course, is how reliable, robust is the system. And testing and quality is something that very, very important. We at Yahoo have nightly tests. This is beyond the unit and functional tests that are in the system. We run about 1,200 automated tests on 30 nodes every night. We are currently working on something called fork testing, where we actually take live data and live applications from our customers, fork them, and then run them against the new versions of our system. Okay, and so that's just coming into place and will greatly improve the nightly testing that we do. Once we have kind of decided, let's say that we want to do a release, like for example, let's say we decide that we want to now do a release 23, what happens then? Basically, QE, there's a QE certification for that release. We run a very, very large variety of applications, very large variety of tests and scale tests on about 500 nodes. For example, in case of HDFS, there's about 92% coverage. We test the balancer, block replication, corruption. We do fault injection. We run, checkpointing. We test all various parts of the system. We do the same thing with MapReduce, test distributed cache, the capacity schedulers, speculative execution, failures, decommissioning, a whole bunch of things. Okay, scale testing. Even though we're only reusing 500 nodes, we put 4 task trackers per node, so we're testing a cluster that's about 2,000 nodes. Okay, we do a whole bunch of performance testing that we run, and then following that, we do our integrated stack testing with, HDFS, MapReduce, Hive, Pig, Uzi, the whole stack, the whole ecosystem that we use. And so at the end of this, we get a system that is actually pretty well tested. And for example, at the end of this, we would probably, for example, call a vote for a .0 release in Apache. In the case of 23, we would consider calling a vote for a 23.0. And this is a system that is actually in pretty good shape. What happens after that is we go into a much more extensive release testing this next phase. So we have what we call sandbox clusters. There are about 3 or 4 clusters, each with 400 to about 1,000 nodes. And we have a lot of production applications that are run there in a test mode. So for example, if you are doing a major release like 23 or the security release, we run these tests for about 2 months. All production projects must sign off before we go to the next stage. Okay, so this is a pretty extensive set of tests. Once this is done, we would consider calling a vote for, say 23.1 on Apache. Okay, so what happens after that is we go into the research cluster. And you should not get fooled by the word research. Although these are known revenue generating applications, but they are production jobs. In fact, they are way more intensive than the production jobs in the production clusters. And we run about 250,000 to about 500,000 jobs every week. Okay, and if it clears that, things are usually fine in production. After that, we go into production and take the system through the release through various clusters. Okay. Now I'm kind of going to switch the tone a little bit and talk about some fundamental architecture changes that we made in the upcoming release, both for MapReduce and for HDFS. In HDFS, the storage layer has actually been a separate layer, but really it only was targeted and coupled with one customer, which was the name node. Okay. MapReduce also, it has compute resources, but was really targeted and very tightly coupled to doing only MapReduce. Okay. And we are changing that. So it is the layers are now a lot cleaner, and it's a one-to-many. So in the case of storage, it turns out it wasn't a lot of work for us to generalize that, to now allow multiple HDFS name systems to run on the top, and therefore it helps with scalability. You could choose to use it for isolation and improve your availability. In the case of MapReduce, we actually had to kind of change the code completely, have the resource scheduler separate from the application masters that manage the MapReduce. And so basically, this separation of concern means that we could scale a lot better and also improve the availability, because a failure in a particular job being managed did not cause the resource scheduler to fail. Okay. And this generic lower layer, for both systems, now means that we can provide first-class support for other things on the top. So for example, in the case of HDFS, we would at some point have the temp storage for MapReduce run directly on the storage system at the bottom. Okay, so we can actually use the storage system to provide a very mini file system, which is much simpler for MapReduce. Okay, We could even consider running HBase directly on top of the block storage and not even use the name node. That's a possibility. Okay. In the case of course, MapReduce, we can things and support other classes and programming paradigms like MPI. Okay. But we can also do things much more radical. So for example, in the case of the name node, it would be a lot simpler now to have a name node that caches the namespace because the layer has been separated. You only need to focus not on the block management, but on the namespace management. This will now be just a few months of work rather than about a year's work. And same thing is true for writing new application managers for MapReduce. And that actually gives us another very big advantage that we can actually provide much better compatibility in the sense that the cluster can now support multiple versions of MapReduce, which is very important for a shared cluster so that customers can upgrade at their own pace rather than having everybody to upgrade, which is very, very critical. Lastly, I want to kind of conclude on the community effect. There are some projects that are done entirely by teams at Yahoo or Facebook or Cloudera. So for example, we focused on append and security and federation and MapReduce.next. Facebook has done the avatar name node, RAID, and High Tide. Facebook has also done a lot of work on HBase improvements in HDFS to support HBase better. So is Cloudera. So there are a lot of projects that are done separately, but there's a lot of joint work. So for example, Yahoo and Facebook work a lot on the name node scalability concurrency. We worked on a whole bunch of small JIRAs incorporated. The work that is happening in edit logs and refactoring of that particular work is joint between Cloudera and Yahoo. The HA work, as I mentioned, is going to be a community effort, and we are really coming together as a community over there. Okay. And so expect to see a lot of rapid improvements in the very near future, further scalability, improved I/O performance, wire compatibility, et cetera. So the kind of conclusion is that Hadoop is successfully crossing the chasm. It is being used in enterprise for revenue-generating applications. It is improving at a rapid rate. Okay, we are addressing many of the issues, including HA. Okay, and what you really have here is the might of a large developer community. If there are features that we don't have currently, it'll happen very quickly. It has been battle tested on very large clusters and a large variety of applications at Yahoo, Facebook, and other Hadoop customers. And it's a level of testing that even the large commercial vendors, okay, cannot match. And so can you really trust your data to anything less? Thank you.
Any work going on the multi-data center support, especially for the MapReduce basic HDFS type of thing?
You mean cross-colo, or you mean multiple cluster?
Multiple cluster across one.
So, for example, MapReduce really only runs within a cluster, so your jobs only run entirely within a cluster. With HDFS, you can mount. We actually have a way of mounting or directly accessing data in other clusters. So there really isn't in Hadoop right now a way to, for example, run a MapReduce job across clusters. Okay, I don't know if that's the question you were asking.
Basically, if I need to support 2 clusters across the data center with the objective that, okay, if one data center goes down, it should automatically roll over to other. So I actually don't want to run MapReduce across.
Oh, I see. Okay. So, for example, at Yahoo, we do have data that is BCP'd on other clusters. So we actually have data that is copied and replicated, and there are tools like DiskCP that actually can copy the data across clusters. Okay, and so we basically have to use something that is built on the top of arranging to copy your data, arranging to have your applications on the other side, and start those applications when you have a failure of one data center. So there's no automated built-in solution at the lower layer. It's something that you need to build on the top.
Using DiskCP.
Using tools like DiskCP to have your data in multiple places, or to actually have your feed data directly loaded into multiple sites.
OK, thanks.
OK, you had a question on there?
Is this on?
Go ahead.
You've described the testing infrastructure for the whole stack that you use at Yahoo. I'm curious, if those tools are going to be made available to the community at large, especially now that Hortonworks is splitting out, or if you're going to concentrate on the newly open source big top from Cloudera, or how this is going to get out to the larger community so we can test our own, maybe different builds and different combinations of stacks.
So, all the unit and functional tests are actually out in the open source, and a lot of the automation stuff is things that we are planning to put outside. But as far as the actual Yahoo applications, clearly those cannot be put outside, or that particular sensitive data cannot be made available outside. Okay, so we'll be continuing to work in partnership with Yahoo and continue to provide stable releases. But yeah, we do want to grow the testing framework overall to make it easier for other people to also directly test.
I don't necessarily mean testing of components, but testing of compatibility of different components with each other, right? So Pig version 10 with Hadoop version 22, etc.
So for example, a lot of the compatibility tests that we are planning to put, we will be open sourcing that.